The problem we'll be working on in this video today is designed to help us apply our understanding of average value of a function and integrating in general to some kind of real-world situation, or at least a word problem of some kind. And in this problem we've got a cube-shaped tank with a side length of 4 feet, and it's being filled with some liquid at a rate of 1/2 cubic feet per minute. If the weight density of the liquid is 50 pounds per cubic foot, we need to show by integration that the average weight of the liquid in the tank over the time it takes to fill is 1,600 pounds. And we know, or at least we're guessing, that the average weight of the liquid over the time it takes to fill the tank is 1,600 pounds because we would assume, if it's filling at a constant rate, that the average weight over the time will be equal to the weight of the liquid when it fills half the tank. So we can illustrate that quickly. We've got our liquid in here filling up half the tank, filling the tank to a height of 2 feet. And then we know that the volume of the liquid in the tank is 4 by 4 by 2. We're multiplying that by the weight density of the liquid, 50 pounds per cubic foot, and that gives us 32 times 50 is equal to 1,600. And now we're going to look at how we can use integration and an average value formula to verify that value that we're guessing. The first thing we need to do if we're going to use the average value formula is to find the function that we're trying to find the average value of. So in the problem we see average weight, and that lets us know that there's a function w of t, the weight function, that we're trying to find the average value for. We have kind of a roundabout process to find the weight function. The first thing we know is that w of t is equal to the weight density 50 multiplied by the volume at time t. And that means in order to find w, we're going to have to first find v. Looking back into the problem, we're not given formulas for volume or weight, but we are given a rate of change in volume. In other words, we're given that dv dt is equal to 1/2, or we can say v prime of t is equal to 1/2. Since we know that the tank starts empty, in other words that v of 0 equals 0, we can set this up as an initial value problem, where we use the derivative to find an original function. So we know that v of t should be equal to the integral of v prime of t dt, which means we have the integral of 1/2 dt. And since the integral of a constant is that constant times the variable, this is equal to 1/2 t plus c. Using our initial value, we get v of 0 is equal to 1/2 times 0 plus c is equal to 0, an empty tank, and that means that C is equal to 0, which lets us move back here to a velocity, volume function with respect to time of 1/2 t. When we think we're ready then to find W of t, we're going to take, like we said before, 50 and multiply it by 1/2 t and get W of t is equal to 25 t. And then we look back at the problem and see that the total volume of the cube is 4 cubed is 64, and the total time that it takes to fill at a rate of 1/2 cubic feet per minute, I guess let's mark this as feet cubed, will be 128 minutes. And we finally have everything we need to set up our formula for W average, or the average value of weight over the time it takes to fill the tank. So this is equal to 1 over b minus a, or 1 over the length of the interval, which we just figured out is 128, over the interval from 0 to 128 minutes of W of t, which we'll go ahead and just fill in here as 25 t dt. Our definite integral here is a chance to use a power rule for integration. So we're going to increase the exponent on t from 1 to 2 and divide by that new exponent. So when we're done, we'll bring this 1 over 128 along and multiply it by 25 t squared over 2, evaluated from 0 to 128. Give ourselves a little bit more room here. Maybe. There we go. Oh, and now we're gone. I'm going to come back. All right. So we have 1 over 128 times 25 times 128 squared over 2 at our upper limit of integration, where we're now evaluating. And if we plug in 0 as the lower limit, then we're just going to end up with 0. So we'll leave that off, close off these brackets, and notice that we can cancel this 128 that's down here in the denominator with one of the ones in the numerator. And when we're done, we get 25 times 128 over 2 is equal to 25 times 64 is equal to 1,600 pounds. So, two ways of doing a problem. Obviously, the way that we tried it first, making a conjecture, was simple, but we were able to verify it by also using our techniques for integrating and using the average value formula.